Welcome back! Good to see you here for another Scilife Academy training session. In this course, we'll be looking at the hot topic of physical sterilization by filtration and chemical sterilization methods. These methods are typically used for medical devices that are sensitive to the high heat used in steam sterilization and for devices that may be damaged by irradiation such as rubbers and plastics. Let's start with filtration sterilization. The process of filtering involves the exclusion of particles and microorganisms from liquid through the use of a permeable material. In general, filters are comprised of porous membranes enclosed in stainless steel housings. The membranes are responsible for separating the particles from the liquids they pass through. The sterilizing filtration method is the best choice for sterilizing solutions that are chemically or physically unstable under heating conditions, as it consistently generates sterile filtrates. It is the only method that does not rely on high temperatures or other forms of energy, such as gamma radiation, to kill microorganisms. Microorganisms are not destroyed by filtration, but they are removed from the product by retaining them in the filter. The effectiveness of any sterilizing filtration process depends on several factors. Here are a few: the type and number of microorganisms, the properties of the filtered liquid, the filter design and membrane polymer, and the filtration process parameters. Sterile filtration can be done using 5 different types of filters: particle filters, microfilters, ultrafilters, nanofilters, and microporous membranes. Generally, particle filters have a porosity of 10 to 200 microns. They are mainly used to prevent membrane microfilters from clogging. They can also remove dirt, bacteria, and most particles. In most cases, they are made from polymers and cellulose fibers. Typically, microfilters are microporous membranes used in intermediate and final filtration of liquids to remove bacteria and yeast. They have pore sizes ranging from 0.1 to 10 microns. This is why they are most frequently used in life sciences for sterilization. They can also be integrity tested, as we will see in a moment. Most sterilizing filters have a porosity of 0.2 microns. However, some studies have demonstrated that membranes of 0.2 microns are not able to remove all microorganisms under all conditions. In some cases, it is recommended to use 0.1 microns filters. Most virus and large organic compounds can be removed by ultrafilters, which have a porosity from 0.001 to 0.1 microns. An organic compound or ionic form of small molecules can be removed by nanofilters with a porosity less than 0.001 microns. Microporous membranes remove microorganisms from the liquid by 2 primary mechanisms: sieve retention and absorption. Sieve retention physically blocks particles that are larger than the pores of the filter. In adsorption, with D, particles are bound to membrane surfaces due to an electric charge. A microfilter is a device that selectively retains microorganisms and particles above 0.1 microns through a process called microfiltration. The integrity test is designed to check the effectiveness of sterility filters before and after use in order to ensure their integrity. It is used to show that a filter has the correct pore size rating, is installed properly, and has not been damaged by the process used to sterilize it. There are 2 types of integrity tests: destructive and non-destructive. The filter manufacturer performs destructive testing for quality control during the development of the product, for qualification and validation studies, and for manufacturing quality control. The integrity test involves introducing a microorganism upstream and ensuring 0 organisms are recovered post-filter. A non-destructive test is done before and after manufacturing the filter. Most integrity tests detect gas flow by measuring the pressure differential across a wetted membrane. Integrity test methods for microfilters include bubble point, diffusive flow, and pressure hold. A sterilizing grade filter is a filter that is capable of retaining a minimum of 10 to the power of 7 colony-forming units of Brevis diminuta per square centimeter of effective filter area. Sterilizing grade filters typically are microfilters of microporous membranes that have nominal pore size ratings of about 0.2 microns, as commented before. Other membrane filters that have a nominal pore size of 0.45 microns can also be validated to produce sterile filtrates under some conditions that require high differential pressures to achieve useful flow. There are different types of filter configurations and processes. One example is a combination of two filters. One filter is used to reduce the bioburden, and a second filter is used to sterilize. Okay, let's move from filtration to chemical sterilization.